Can you change the camera to this direction? Okay. We have x. Remember the consensus theorem. It was, I think it was in terms of A, B, C, if I don't remember right. But I'm going to call x, y, z instead. X plus y, we have x bar z, and plus y, z. Okay. And the theorem says that this is equal to xy plus x bar z. Okay? This is the claim, by the way. So you can see that this is the part that vanishes. Okay? As a matter of fact, because this is identical to this term, this is identical to this term, and this part goes away. Okay? So how does that happen? This is the consensus term. This term. Okay? And so we look at this as xy plus x bar z. So the only way we can deal with this consensus term, we have to extend it. Okay? How? We can, for example, multiply that with x plus x bar, for example. Okay? Because this is what? 1. And you can multiply anything with 1. In other words, AND. In the logic operation AND. Same as multiplication in binary domain. So there are the two different things, but means the same in binary domain. Okay, so use distribution law, of course, now. So we got xy plus x bar z plus xyz plus, I get this x in the front because of the commutativity law. Okay, so we got x bar x prime yz. Okay. Okay, good. So when I look at this, I have xy here and xyz, right? So I can connect them, right, using distribution law. What does that mean? That means xy plus 1 plus z, right? Again, using distribution law. That one and that one goes in the same bin. How about these two? Again, the same way, plus. You got x prime z, and I have 1 plus z, right? Okay? Y, right, yes. Right. Thank you very much. Okay? So what is this? 1, right? Because if you add 1 to any digital data, right, 0 or 1, binary data, you get 1. Okay? And here, this is also 1. And if you multiply 1 with any Boolean logic, you get the Boolean logic itself. So you get, again, these are all comes from all these postulates, from the postulates or theorems we already proved. So this is xy plus x prime z. Okay? And this is the end of our proof. We usually use QED to represent end of proof in Latin. Right? Okay. You can actually now, my question to you, you can use, of course, the same type of logic to prove the dual of this. Okay, do you remember the dual definition of dual? If you got, for example, x plus y z prime, if you take the dual of this expression, all you have to do, change ors with and change ands with or. Okay, in other words, you get xy plus z prime. This is the dual. I usually use D to show the dual. So if you take the dual of the left-hand side and right-hand side, okay, then it doesn't change anything. The equality still stays. Okay? So if you take the dual of this and dual of this, for example, let me show you the dual of this to you. This is x plus y multiply or and with x prime plus z. Okay? That's the dual. And same here, and you can show that equality still stays or holds. Go ahead. I can't understand. Can you tell again?
We must take both sides, right?
Yes. Yes. You have to take the dual of the both sides of this equality to be able to assert that this equality still holds, right? Because taking the dual changes the logic. Okay? Taking a dual changes the function, the Boolean function. This is the Boolean function we have. Okay. Okay. And also, you have got a question?
It's prime plus
Which one? Did I did something wrong?
X prime plus
Which one? You talking about this one? So this is x plus y.
yx, y not x prime.
And that's x prime plus z. So we don't change the primes or the letters itself, original letters itself, but only the operations when you take the dual, all right? Now coming back to question.
Yeah. When x and x plus x prime at the first line of the solution. Right. Yeah. When you pick x, what happens if you pick y or z?
You could, but I did that specifically to be able to get all these simplifications. This is the, let's say,
What did you consider that? When you decide,
I'm not sure I get the question. Do you mean I can replace this x plus x bar with y plus y bar?
how did you decide that you pick x? Like,
This is the proof. In other words, you know, you can try YZ, but you already have YZ here. The reason that I inserted X here, so that I have X, Y, Z, all three in the same Boolean expression. Okay? We'll come to discussion of POS and SOP forms of a Boolean expression later, and you will realize that having all these three inside this AND operation will give you more, specific observation about the function. Okay? You could, if you want to try, I would suggest you when you get back home, you try y plus y prime and z plus z prime and see if that goes anywhere. Okay? Then you will understand why I choose x plus x prime here. Okay? All right. Okay, so let me erase. How many minutes do I have? Okay, we got more than 20. Okay, good. So let me erase this part if you're okay. Right. If you got any other question, please go ahead. These are, I know, more mathematically sophisticated part of the class, and you may get sleep sometimes. That's normal. However, we'll get to the exciting part of the class, in a couple of days, I assume. But these are, fundamentals. So I really recommend that you try to learn this stuff, because this is the deep part of the class, let's say, mathematically. So finally, I'd like to talk about the complementation. If you remember the complementation, if I give you x, for example, the complement of that operation produces x bar. You already know this simple operation. If x was 0, then x bar would be 1. If x is 1, then this would become 0. Okay? That's the complementation operation, and if you remember, we got the following notation for negation or not operation, right? Or inverter. These are all the same name for the same function. These are different names for the same functionality. Okay? Okay. Oh, of course, the expressions that we will be facing are not that easy. We usually have a Boolean expression, a complicated Boolean expression, such as the one that you have in your slides. Let me just quote them, which is AC plus B prime. You got D, and then you got AE, and then you got another complementation. All right, so let's suppose this is my function f. Okay, and I'd like to find, let's just suppose that this is my f, then I'd like to find f prime. Okay? So I erase the prime here, and then let it to be equal to f. Okay, actually you can erase either these ones as well, right? Then you got f, then I'd like to know the complementation of f. Okay? All right. The way that you approach to this problem is to use De Morgan's law. Okay? If you remember De Morgan, if you got AB, for example, in parentheses, if you take the complement of that, what you get A prime multiplied with B prime. Okay, the rule is very simple. You change, whenever you see plus sign, you change it to dot. Whenever you see a dot sign, you change it to plus. And all letters that you see inside the expression, you get the complementation of those letters. In other words, if it's A, it becomes A prime. If it is A prime, if it was A prime, then you get A. Because complement of the same a letter or expression, you get the same thing. Okay? Again, this was a theorem that we proved earlier. All right? So we will use that rule in here. So let's start, if you like. So this is the biggest expression we probably have seen so far. So I'm going to explore this step by step and slowly. So we got this old expression here, and we'd like to learn about the complement of that. So I'm going to treat this. I'm going to treat this as, first of all, let's say this is my x, and this is my y, and this becomes identical to this form, right? So that means actually I have x prime, okay? X prime, which is this prime, right? So we got AC plus B prime, D, and then I have a parentheses complement. This is my x prime, plus this is y, and this says y prime. So I have AE prime.
Not plus.
It should be dot.
Oops. Thanks you very much for catching my errors. You know, when you write something to a piece of paper, you usually realize it, very quickly. When you write it on a board, it's sometimes really hard to catch it. So thank you very much. Okay, I have that. So do you have any problems with this? I just applied this rule here. Okay. So now I applied the rule, same rule, now to this, because it's still a big expression here. So I'm going to say this is my x. Now this is my y, right? And then I get what? Complementation makes this x prime, right? So this is prime now. AC plus B prime, prime. Now that becomes plus. And we got y prime, which is B prime, right? Okay. And now this is still dots, right? It doesn't change because I'm looking inside the expression now. So maybe I can use a curly bracket here to put a dot after that. What is this? A prime plus E prime, right? Okay, good. All right, I still have something here that I can use for De Morgan's, right? So now let me just, this is my x now, and this is my y, right? So that becomes a C prime, right? This becomes dot. This becomes B, right? Directly, because B prime prime gives you B. Okay? I think everybody happy with this? Right? And then I have plus D prime. And then I have this thing, and then multiplication, and I have A prime plus E prime. Okay? And I still have something here that I can use the Morgan's law, right? So let me just carry the here. I have A prime plus C prime, right? And then I have B and plus D prime. And then multiplication or add-and operation with A prime, B prime. Okay? That's all I can do with the De Morgan's law. Now the time to apply distribution law, right? So you can apply the distribution law now. Right? This is A prime, B plus B, C prime, let's say, and plus D prime. Okay? And I have A prime plus E prime. All right, good. I can still use distribution law. Now it's a kind of bit more convoluted because now you have this thing, that thing, right? You got actually 3 multiplied by 2, 6 different terms. So let me just write it down here. We got A prime B and with A prime. What does that mean? You got 2 A primes. Do you remember this? X dot X? X, right? X dot X is X. So which means you got A prime B, A prime, so that means you just have A prime B. Okay? How about this? A prime B, E prime? Well, you cannot do anything about that, so this is going to be A prime B, E prime. How about the second one? A prime. Yes, you have to deal with all these possible cases, particularly when we get to SOP and POS. We'll be bothering with all these, term-by-term expressions, and it's kind of a headache. Okay, we got A prime, B, C prime, and then we have B, C prime, E prime, right? How about the last one? We have A prime, D prime, and E prime, D prime, E prime, let's say. Okay? And you have plus sign. Okay? This is your expression. This is the final expression, okay, that you are supposed to get. However, there's something that I'd like to tell you about this expression, is that we apparently have 5 inputs to this, let's say circuits. Okay? So this f function is, suppose we have a box here, we call circuit, digital circuit, and you have 5 inputs apparently, right? Because we have A, B, C, D, and E. Okay, we have A, B, C, D, and E. And circuit computes, of course, let's suppose computes f prime. Okay? Computes f prime, and where f is given by this expression. So this f prime, and we calculated it, right? This is your circuit. And do you know how to implement this circuit using AOI gates? And or an inverter? I mean, it is complicated, right? But you know it. Why? Because these plus signs are OR gates. These dots here, they are not shown, but they are dots. These are AND gates, and those primes are NOT gates. So you can pretty easily draw that logic diagram. Of course, it's going to take a lot of gates, so don't worry about it at the moment. But you should be able to. Okay, based on our Monday's meeting, if you remember. Okay. Now, let's come back to this circuit. And I would accept, for example, I'm going to define some form of a Boolean function, which means each one of these terms, okay, you can see it, right? I mean, you may not see, those people at the very far end may not see it, but this is A prime B, but there is no C, D, or E in this expression. Similarly here, it's A prime, B, and E prime. There is no C here, for example. There is no D here, okay? And similarly here, and here, and here, and here. And so let me tell you the point that I'd like to get to. In fact, you can express F in terms of those products. And those products will have all A, B, C, D, E, all of them inside. This, I would say, the simplified version of that more general form. In that general form, you will have, for example, this can be, remember, for example, can you add C plus C prime here? You can, right? Because it's just 1. Multiplication by 1 with this expression, doesn't change anything, right? Logically. How about you can also add D prime here, right? Would that change anything? No. How about E plus E prime here? Would that change anything? No. Use the distribution law, you get A, B, C, D, and E. All of them. Do the same thing here, 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 here. Of course, there will be some common terms which will cancel out because of the following formula. X plus X is X, right? So you don't need to put the same expression twice. So just get rid of them. Then you will get an expression where every single term between plus signs would have A, B, C, D, or their complements. Okay? That form has a special name called SOP, or sum of products. Okay? Now I'm going to discuss that. The reason that I introduced that kind of form is very crucial in digital circuit design because it gives us a good way of comparing circuits. Okay? By just looking at their Boolean expression, you will realize that, oh, that term is here, but that term is missing, so these two functions cannot be the same, etc. Okay? That's one of the things that I would like to open up. Go ahead. We've got a question?
Then this is the output, right?
Yes, this is the output, yes. You calculate F prime. So you have a circuit that computes, it gets these 5 inputs, it computes F prime, and this is your F. Okay? And this is the result, F prime. Okay? And you may, for example, be dictated by your boss to use AND or an inverter. Okay? So you will use them. And of course, when we get to the design, by the way, you will never use AOI gates, unfortunately, because they are costly and logic operations. We will mostly use NAND gates, which is called NAND technology, and NOR gates. Okay? For example, solid-state drives are based on NAND technology. Why? Because it's cheaper. Costly, from cost perspective, it's cheaper. You can pack, for example, 100 NAND gates in place of one single AND gate. So which one would you choose? Of course, NAND gates. Then we will actually learn about how to transform this into an expression which would be more NAND friendly. Okay? We'll learn about that as well when we get to the design. All right. So the main purpose of that question was to teach you De Morgan's law. Is that clear to you all? De Morgan's? Any questions about De Morgan? No? Okay. Then let me briefly introduce you to our, let me just introduce you a couple of more gates, okay? Couple of more gates. Then I'm going to talk about SOP and POS in detail, okay? Since I've got only 15 minutes left, I'll be as brief as I can. All right, so let me erase this part of the board. All right. All right, so let's see. Okay, so these are known as canonical forms. Canonical forms. There are two types of canonical forms. One of them is called sum of products. Okay, that's called SOP. Okay, and the other one is called product of sums. That's called POS. Okay? As you may expect, this sum of products, meaning that you got multiplications like A, B, C, or C, D, E, whatever, and then you have the sum of them. And you have the product of sums. This is actually parentheses. Inside the parentheses, you have a sum expression, and you have got multiplication between the parentheses. So let me show you some examples here. For example, let's suppose we have a circuit just like that, this one, that I showed you earlier. This circuit now has two inputs, A, B, okay? And there's a function that is implemented by the circuit, F. Okay, and I express this F in terms of A, B, but I'm using sum of products. So let me just show you an example. A, B prime plus A prime B. That's just one example. Is it in SOP? Yes, because this is sum of products, and each product has both A or B or their complements. Okay? For example, if F was A plus AB prime, this wouldn't be in the SOP form because this has no B in it, or B prime. Okay? This is not in SOP form. This is the SOP form. Okay?
Can it be just one element, like AB?
No. As I said, if F is A plus B, you're asking this one? Yeah. This is in SOP. Yes, I've actually misunderstood you. I thought that you said A plus B, so that's not. This is of course in SOP form because you got it one term, single term, and it has both A, B, or their complements. However, if you have A plus B, this is not in SOP form because each term has a missing item. This, for example, doesn't have B or B prime, and this has got no A or A prime. Okay? Okay, so this, I think you guys get the idea here for the SOP form. So let me just draw a simple table here to teach you a more maybe formal way of defining new terminology about the SOP. Okay? Okay, here we go. We have the following table. Again, I'm still stuck with two inputs, so because two inputs is a good way of starting discussing such things. All right, so here I have the binary. Okay, so in this table, I'm going to now explore all these possible cases. For example, for two inputs. Okay, so we got AB, right? We got AB. So I'm going to now start with A prime prime, I have A prime, B, I have A, B prime, and finally we have A, B. Those are all the possibilities, right? There are no more possibilities. Now, this, for example, function has only two of them, which is A, B prime and A prime, B, right? These two. All right, good. All right, so now, I'm going to now map them to a specific binary because we don't have ABs in digital hardware. We have zeros and ones. Okay, so I'm going to just say A prime, B prime is just 0, 0. And this is 0, 1, this is 1, 0, and this is 1, 1. And I'll come to that why this is the case. It will actually help us with the rest of our calculations. Okay? All right, so now I'm going to have, of course, let's suppose that this is A, this is B. Okay? These are just like, inputs that I've drawn in the circuit here. So when A is 0 and B is 0, what is A prime, B prime? 1, right? Good. How about if A is 0 and B is 1, what is A prime B? 1. It's 1. How about A is 1, B is 0, what is A B prime? Again 1. And then A is 1, B is 1, what is A B? 1. Right? 1 and 1 gives you 1. Okay, so did you get why I mapped these 0, 0 to A prime, B prime, and 0, 1 to A prime, B, blah, blah, blah? Because each one of these terms would correspond to a 1 if the inputs are these corresponding elements. All right? Digital elements, 0, 0, 0, 1. Okay, now I'm going to define any one of these to be mean terms. Mean term, okay? And correspondingly, I'm going to also define max term. Max term. What is max term? Max term is actually the complementation of this, which is A plus B, or the complement, or if you take the complement of this using the Morgan's law, you get A plus B. So I just take the complement of that. So this is A prime, sorry about that. This is going to be A plus B prime. This is A prime plus B, and this is A prime plus B prime. Okay? These are just the complements. And the max term is actually defined to be the complement of mean terms. Okay? That's the relationship between them. And don't ask me, why did you define that way? It's just definition. It's in every digital book you can, pick up from the library or a bookstore. Okay? That's how people define it. And it will be just convenient for us to use the max terms and mean terms in this defined way. Okay, and the corresponding decimal numbers for this 0, 1, 2, and 3, right? Using our original 8421 code. Okay, so I'm going to have, of course, these are kind of complicated, particularly if the number of inputs, not just 2, but 3, 4, 5. If you would like to express this in terms of 5 inputs, 6 inputs, it's going to be very complicated. So instead of that, we're going to be using small m0 for the first mean term, and then m1 for the second, m2 for the third, and m3 for the fourth. Okay? So small m means mean term. How about this? This is max term, and I'm going to use capital M0 for the first max term, and capital M1, M2, and M3 to be able to illustrate the final max term, A prime plus B prime. Okay? Okay, so after having these definitions, now I can come back to my circuit here, F, and express this F in terms of these mean terms and max terms. For example, F actually equals AB prime. What is AB prime? AB prime is M2 plus M1, correct? Because these are the mean terms that I'm using. All right? Okay, so let me just draw the truth table of F for you, all right? So I have, do you remember the truth table? Yes. Actually, we've run through that, but I am going to show you the details just in case that you may not remember it, because we're going to be resorting to that technique over and over again. It's very important. We have 0, 0, 0, 1, 1, 0, 1, 1. Okay, same way that I just shown you. So F is what? AB prime and A prime B, right? The way that we learned how to use truth table is as follows. So don't worry about the mean terms. I'm going to come back to the connection that I'd like to draw here. Instead of first calculating F, we first have to calculate these terms, right? Which is AB prime right? And then add A prime B here. So let's calculate the corresponding logical values for AB prime. Can you tell me what AB prime is?
0, 1.
So the first row, 0, 1. AB prime.
Is it 0, 1?
Only one.
I'm asking you to get A and end with B complement. It is 0, right? Good. Start doing it in your mind, okay? Because these are very simple expressions, so you have to get to that maturity at this point. Okay, just work it hard in your mind. Okay, how about 0, 1? If A is 0 and B is 1, what is A and B complement? 0 again? Yes. Okay. How about A is 1 and B is 0? What is AB complement? 1. Right. How about 1, 1? 0. Okay. Is that a surprise? Not actually, because this is a mean term, and mean terms can only bring out single one at a particular position 1, 0. You look at this being 1, 0, it's AB prime. Okay? So AB prime actually produces at this particular row 1, 0 and nothing else. And nowhere else you can have 1. Okay? This is the, the definition of mean term. How about this A prime B? 0, 1, 0, 0. Because its particular row is 0, 1. If you can check it here, 0, 1 is A prime B. Okay? Now, finally we get to F. Right? Okay, let's get to that F. That F is just or of these two columns, last two columns. Actually, this is the main reason why we calculated these two columns in the first place. Just to get to F. Right? So, what is F?
0, 1, 1, 0.
0, 1, 1, 0. Everybody agrees with that? Okay. Now F is expressed in terms of two mean terms. You see the mean terms? Actually, when you have F, of course, this is very easy to, comprehend. Just two mean terms, and you got two columns. If you got, for example, if you're dealing with 5 inputs example, let's say 5 input function, and you got 2 to the 5 possible mean terms, right? Which is 32. And I can actually write F by giving you 10 of those mean terms. That actually means there are 10 columns you calculate, and then you finally end up with the following F. Okay? So this is the connection between the mean terms. It basically gives us a better or easier way of expressing things. Okay? So this basically tells you, first row, if you look at the rows as 0, 1, 2, 3, this basically tells you that M1, which is this row, right, and M2, this row, is 1 in the truth table. The rest of them are 0, 0. Okay? So there is a one-to-one mapping between the canonical form, SOP, and truth table. Okay? There's a one-to-one relationship. If you know the truth table, you can come up with the mean terms. If you know the mean terms, you can come up with the truth table directly without considering those two columns. You don't need these two columns. Okay? I want you to go from back and forth between these two, okay, as if you know these columns. So don't worry, you don't need to worry about the columns. I think I ran out of time, I guess. Right? Okay, let's stop here. I'm going to continue my discussion in SOP and POS next time. Ya handout'ları aslında benim çözmem lazım. Tamam. Handout'ları ben aslında çözmem lazım. Ama zaman bulamıyorum.